Working as developer advocates at IBM India, our upcoming team of DevOps spokespersons are also members of the IBM Developer Ecosystem Group. Rachana Vishwanathula sets her tech focus on artificial intelligence, and her mission is to enable developers on various technologies. She also works with startup communities and has delivered immersive and engaging tech talks and conferences on a diverse set of technologies including data and AI, IBM cognitive services, and security. Joining her at today's presentation is Saurav Rajguru, who is a tech evangelist at IBM, coming with strong 6+ years of experience in the industry. He is responsible for bringing one IBM technology value to the customers directly. He engages with the developers at large enterprises, partners, ISVs, and startups, largely to help them adopt latest technology trends around cloud native, data platforms, and AI on IBM Cloud. And now, ladies and gentlemen, they are here to give us a deep and clear understanding on how to secure container images and leverage Kubernetes native CI/CD pipeline in the DevOps world. Without much further ado, please join me in welcoming on our screens right now Ms. Rachana Vishwanathula and Mr. Saurav Rajguru. A very warm welcome, Rachana and Saurav. Over to you guys.
Hello, everyone. Good morning, good afternoon, and good evening. At the outset, I'd like to just say that we're hoping that all of you all are well, happy, and safe. Welcome to this session on securing container images and leveraging Kubernetes native CI/CD pipelines in the entire DevOps world. I am Saurav Rajguru, a developer advocate at IBM, and I'm joined by my colleague Rachana Vishwanathula, who's also a developer advocate and a fellow IBMer. So to get started with understanding Kubernetes native CI/CD pipelines, we have to look at a new project that has been GA'd or open sourced by the Continuous Delivery Foundation about sometime around last year, around March of 2019, which uses the Kubernetes style resources and for declaring the CI/CD concepts, which is what actually means is that the Tecton as a project or as an application runs as a Kubernetes resource by itself, which is kind of divided by using the custom resource definitions in Kubernetes, which is actually the pods and the deployments and replica sets, which is what it kind of leverages. It kind of stands on four guiding pillars, which is the declarative model, in which the concepts of YAML in Kubernetes is used. It's composable and decoupled because you can add back and forth concepts or components of Tecton and create a complete pipeline, complete CI/CD Kubernetes based pipeline. It's also called cloud native because it's accessed just like kubectl is accessed from a client and server architecture through the kubectl CLI. Tecton is also accessed by a TK and CLI, and which is why it's and it also runs as a container resource, and which is why it's running on a guiding principle of being a cloud native software or application by itself. So to dig a little deeper into Tecton, it stands on two particular concepts of Kubernetes, which is the custom resource definitions, which actually is leveraged to create a custom resource called pipelines, tasks, and steps. These are the three guiding functions or components of a Tecton platform. And the second is around having something called as controllers, which is kind of very imperative to Kubernetes, by which you can archive your desired state, act on resources to create, update, and delete a certain set of resources on Tecton. Together, these two components create something called as a declarative API called the TK and CLI, and you can talk to your cluster, you can talk to your Kubernetes cluster through this API and work on your custom resource definitions, which are your pipelines, tasks, and steps, right? Moving ahead, the three conceptual pillars of Tecton, which is a step, a task, and a pipeline. A step is nothing but it's the smallest building block. We can consider it as a container that is running on the platform, on a Kubernetes platform. And generally, it's used to create or write commands, arguments, and specify images that will be given into a pipeline. A set of steps or a sequence of steps rather is called a task, which is kind of reusable, or we can call it composable, because a step like hello world can be reused in a multiple number of pipelines at the same time, which is why and task is something which is the smallest unit of resource. If we compare the smallest of unit of resource in Kubernetes, which is a pod, task is the equivalent smallest unit of resource in a tecton, and task runs as a pod. The initialization of a task would be called as a task run. uh, Typically would require some sort of input like a GitHub repository, would spit out or some execution parameters, and would spit out some sort of images and other things once the pipeline is kind of over, right? And a sequence of tasks, if it's kind of expressed sequentially or concurrently, however you may write it, will be called as a pipeline. A pipeline is something that we see as a holistic tecton pipeline, CI/CD pipeline, and and all of them have multiple number of tasks which are like a pod, and they run concurrently or sequentially. The instantiation of a pipeline would be called as a pipeline run, right? And this would require specific amount of inputs like a GitHub repository. Certain times there are some parameters that you want to input on some specific output, or location to where a container image that is finally coming out would be deployed, or where would you deploy a container image into a Kubernetes platform. So these are the instantiation of a pipeline. But typically, if you look at it from an example of a pipeline, where you may have steps starting from linting all the way up till publishing images and deploying. If you look at it from in a tecton view, the entire pipeline would be called as a deployment, right? And the group of tasks or the sub activities that a pipeline is supposed to be doing will be recognized as a pod. Now, this is coming with a significant merit when your entire application or your entire CI/CD pipeline is running as a Kubernetes resource. Because when you're running something as a pod, if you look at the merits of Tecton, I would like to highlight three of them at this point, right? One is that you can significantly achieve scale, because if your Kubernetes resource or your CI/CD pipeline is itself running as a pod, the concept of auto scaling and auto healing automatically applies on your CI/CD resources as well. So imagine a hello world task being called 5,000 or 10,000 times. The act of Kubernetes resources or the controller which is watching on top of this would immediately start scaling and healing as and when there is as and when there is a resource needed. All that is it is depending upon is the infrastructure below, and not the CI/CD application per se, because we've been using certain CI/CD applications like TeamCity, Travis, and Jenkins, and so on and so forth, all this while. But all of them have application, concurrency dependencies, if I may put it that way, and all of that is kind of alleviated now. And because your entire CI/CD pipeline is running as a Kubernetes resource, as a pod, as a deployment, and they can be scaled automatically. By default, if the CPU memory usage exceeds 50% of your cores and memory, it would automatically scale and heal as it would do otherwise also. So the pipeline entirely is running as a container. It brings standardizations like YAML and CLI and Web UI, which kind of remove the effort of human capital, right? And it reduces the significance of a resource engineer or a software developer or a DevOps engineer per se to kind of learn all of these technologies, which can take a lot of time. So at this point, I'd like to take you through a quick walkthrough of a Tecton pipeline on IBM Cloud, which would look something like this. There is something on IBM Cloud. There is something called as the tool chain. Tool chain is a service that helps us, integrate all of these different tools, integration tools, kind of create an entire pipeline. The first, and in addition to these four concepts or four modules that we see, which is a GitHub repository from where our code will be pulled from, a pipeline private worker, which is going to create the builds of our container images from source code, and the delivery pipeline, which is going to run the build, test, and deploy entirely on a Kubernetes native platform. The fifth that we'll need is a Kubernetes service on IBM Cloud, which is called as IKS, which is the IBM Kubernetes service, which is where the entire deployment of the build image would take place, right? The third is a GitHub repository, which is hosted on IBM Cloud on a private GitHub server or a Git server. The most important part to note here is the Tecton folder, which is where are the pipelines and the YAMLs and the tasks folders the task.yaml that we saw earlier is kind of saved here in this form. And it would always be triggered starting from a pipeline.yaml existing in a .tecton folder in a Tecton environment. The sixth is a delivery pipeline private worker, which is kind of private or proprietary to something on IBM Cloud. This is a worker that is kind of attached to your Kubernetes cluster, where we will finally deploy our built image right after the end of the pipeline. But what happens in a private worker is where actually the build process goes through. It goes through a multiple number of checks, the build processes that you write. And finally, when before the container image is pushed into a registry, the private worker is where the image is kind of built. The last is something called as last and the core part is something called as the Tecton pipeline. It is built on a service called delivery pipeline. And essentially, if you see, it's very similar to any other DevOps pipeline that you will see, that how many number of runs that have happened. We'll come to this in a little while. But let's see, prior to that, there are about 4 tabs that we need to kind of fill or provide before a Tecton pipeline could be initiated. The first is the definitions. Which is where the repository name is kind of added and which branch or tag or path and the path which you want to trigger. The second is a private worker, which we mentioned earlier is probably the place where the build and the other activities would take place. The triggers, on what event would you want the Tecton pipeline to get started? So we've created 2 of them here. One is a manual trigger and another is a Git trigger, which would happen on a master branch of the same Tecton repository that we saw earlier, and it would happen whenever there is whenever a commit is kind of pushed into this repository. The last but not the least is a set of environment variables that every task or a step would require before they get started. Though different tasks need different kind of inputs, and these inputs are ranging from API keys to cluster names to cluster namespaces, and which container registry would it be pushed into, and so on and so forth. And we can always we can always do a manual trigger because we've created a trigger type of manual trigger and always initialize a run like this. At this moment, we can go back to our pipeline run and see something that has already been executed a while back. And if you look at it, it looks like a very traditional DevOps pipeline, CI/CD pipeline. But each of these resources are running as a Kubernetes resource, as a pod, as a set of deployment. Each of these steps of building, or checking a pre-build check, cloning a repo, building, and then finally deploying the entire sample application. Sample Kubernetes application into a Kubernetes cluster is actually working as a Kubernetes resource, which is why the entire concept of auto scaling and self-healing can work. But to show you a little depth into what the Kubernetes resource on the Kubernetes service is going to create is something like this. When you try doing a kubectl get namespace, a namespace of Tecton pipelines is kind of created in your Kubernetes cluster because we installed a private worker. And if you get a little deeper into the Tecton pipelines, what you see is range of pods and replica sets and controllers of the Tecton application and the platform that is created and up and running, right? And we saw that we initialized a pipeline run, and when you see, and we kind of deployed into a namespace called prod, and which is where the Tecton pipeline after the run of creating the build and creating the container image and pushing it into the container registry, has sort of deployed the application into a namespace called prod. And we can see that there are pods and services related to the Hello application that we kind of created. But segueing into our other concept today that we want to learn about, securing container images. We saw that the entire native pipelines, what advantage that native Kubernetes pipelines using Tecton can create. But once you create, but in the gamut of security, if you see, uh, we have container images being created every now and then. At the end of every DevOps pipeline, we create and push container images into a container registry, whether it be Docker Hub, whether it be a registry service within IBM Cloud, or any other private registry service that you may use. But all of these come with their own set of security issues and vulnerability, and that's what we'll see in the next segment, for which I will hand it over to my colleague Rachana, who would take us through the vulnerabilities and the security issues and what kind of protection we need to have over our container images before they are kind of ready to be deployed.
Hello, everyone. And let's actually dive into the security concepts around the container deployments. And as part of enterprises' IT digital transformation, applications have expanded from traditional bare metal servers to virtual machines and now to containers. This is driving containerized app development. With that, enterprises are faced with a key challenge. How do we ensure that the containerized applications are secure? So containers make it easy to ensure consistency across environments and multiple deployment targets like physical servers, VMs, and public or private clouds. This helps teams to easily develop and manage the applications that deliver business. Because of this, app modernization and migration of cloud is significantly increasing container adoption. And it is expected that in the next 2 years, 89% of increase in container usage is expected. Despite the high adoption rate, container security continues to be a concern for IT professionals, and 50% of the IT professionals cited security as primary issue with the container strategy. So these are some of the DevOps and security for agile and cloud native environments. These are some of the best practices that are noted in the recent years. Security by design, culture, and practice. It is a successful application security program that starts with the people culture that led to secure and best coding practices. Then we have shift left security and development. This is one which practice that defines and embeds security and compliance within the SDLC cycle. Core security controls early, which will implement core controls across data, identity, network, endpoints, and containers. And we have to make sure that we are continuously validating and performing offensive testing. CI/CD delivery automation, such as Red Hat Ansible, we have to establish a robust DevSecOps toolchain while helping automation of deployment and security controls embedded into the deployment of new workloads. So let's dive into the actual security concerns around container environments. These are the 5 major risk areas that we observe in a container environment. It starts with images. Containers are built either using a parent or a base image. Images are useful for building containers because you can reuse the various components of an image instead of building an image from scratch. However, like any piece of code, images or their dependencies could contain vulnerabilities. And then we have registry. For developers, the quickest and easiest way to incorporate a standard open source component in an application is to pull an appropriate image from public repositories or public registries. And when you do this, by necessity, you're trusting that the registry is maintaining at least basic level of security regarding the contents of image. And orchestration. The orchestration layer of a container security focuses on the environment that is responsible for day-to-day operations of the container. There are multiple moving parts in an orchestrator, such as Kubernetes. This makes it more challenging to secure, not only because of the number of components involved, but the way in which those components interact. Some communicate via API, others communicate via file system. All the potential points of entry into the orchestration that must be, we have to make sure that these are addressed. And containers themselves. Besides the entities such as apps and images they hold, containers themselves are considered vulnerable to security risks through container runtimes that manage the containers. A vulnerable runtime could expose all the containers that it runs and also the host OS to the potential security risks. And then we have host OS. Host OS is where the environment is perhaps most important layer of the stack, because an attack that compromises the host OS could potentially compromise entire environment. A container environment introduces new threat vectors. In the threat surface that we've seen in the previous slide, each threat surface presents with new threat vectors that could possibly be the reasons why an attacker how an attacker could enter into the system. It could be as simple as a configuration issue, but it could move towards a potential uh, security takedown. If you consider images, we have image vulnerabilities, configuration detects, and sometimes if you are pulling an image from a public registry, there are untrusted images. And similarly, the issues change with each threat surface. If you're talking about securing a registry, we'll have to ensure that insecure connections are not there and there are no stale images in our registry, and make sure that we are not exposing the other images in the registry to something else. And similarly, each threat surface, each risk area presents us with new threat vectors. These are some of the threat vectors that are observed in the recent times. And security services should cover all the container risk areas. Starting with image, we'll have to make sure that the securing of image is done. Application images are among key vulnerable areas for security risks in a container environment. These images can be outdated ones, insecure versions of software, or applications that are carrying bugs, and those that contain hidden malware, and those that are loosely configured. Moreover, these images often carry along authentication keys and certificates. To address this risk, we'll have to do design validation, we have to detect configuration defects, and define policies to block the instantiation of insecure images. Securing the registry. So when we are accessing from a poorly configured registry, the access should happen through encrypted and authenticated connections. Also, the registry should undergo continuous monitoring to ensure all the states, all the stale images that offer scope to vulnerabilities are cleared. We should ensure audit processes, implement and the implementation of secure connections, and we'll also have to develop policies for effective authentication to ensure the registry is secure. Then we have orchestration. It is recommended that tight access control to cluster-wide administrative accounts through effective authentication methods such as multi-factor authentication beyond just the usual password authentication. We'll have to make sure that the segmenting of containers by purpose, sensitivity, and threat posture, it usually provides defense in depth. Overall, orchestration platforms should be configured to features that make them facilitate a secure environment for all the applications that it's running. Therefore, it is recommended to implement role-based access policies, proper API controls, and design and implementation of workload security zones. Securing the containers. The most common security issue with the containers occurs when container runtimes that manage containers themselves contain vulnerabilities. A vulnerable runtime can expose the container it runs and also the host OS to potential security risks. Given the flexibility that containers enjoy through dynamic IPs over the network, there is a need to identify network anomalies in such environments and apply relevant filtering tools to address any possible vulnerabilities that might come. We should ensure that the vulnerability management will have to monitor and help control the unbounded network access, detect and fix insecure container runtime configurations. Securing the hosts. Host OS is a key to successful container environment. Given the fact that it lies at the lowest level of container architecture, it is the most critical target to secure. It is the most critical target to security threats. A compromise of a host OS can lead to the compromise of entire containers that are running on it. Host OS should undergo continuous scans for vulnerabilities and requires any updates that should be immediately applied. This is not just at the level of container runtime, it should also be done at the lower level components such as kernel, etc., which are also the key secure container operations. Proper configuration is also important to the security host OS. It should be run as an immutable infrastructure with no data and application level dependencies. This makes host OS highly reliable and effective in functioning. So some of the practices that we use while we are running Docker images are Docker image signing. So when we are transferring data among network systems, trust is the central concern. In particular, when communicating over an untrusted medium such as the internet, it is critical for us to ensure the integrity and the publisher of all the data a system operates on. You use Docker engine to pull and push images to a public or private registry. Content trust gives you the ability to verify both the integrity and the publisher of all the data that is received from a registry over a channel. Docker Content Trust provides a strong cryptographic guarantee over what code and what versions of the software are run in your infrastructure. Docker Content Trust integrates with something called the update framework into Docker by using Notary. The update framework and Notary are the open source tools that provides trust over any content. When a publisher who is using Docker Content Trust pushes an image into a remote registry, Docker engine locally signs the image with the publisher's private key. And when a user pulls this image, Docker engine uses publisher's public key to verify that the image is exactly what the publisher created. It also ensures that the image wasn't tampered with and that it's up to the date. If we make sure that we implement this as part of toolchain, we are simply automating the entire process. So if you see, this is a sample toolchain that has two steps. The first one, the init Docker Content Trust stage, starts DCT by using the information that you provided when you set up the key management. The stage also allocates keys and provisions them to be the delegation keys that are used to sign the Docker images. And the second stage is where we set up Iks Runtime Enforcement in the deployment cluster. This stage creates an image enforcement policy that is applied onto your Kubernetes cluster. The stage also specifies that an image can't be deployed until the signatures are found and validated. So you can control where the images are deployed from. You enforce the vulnerability scanning policies and ensure the content trust is properly applied to the image. If the image does not meet your policy requirements, the pod is simply not deployed onto your cluster or updated. So CISE, Container Image Security Enforcement, retrieves the information about the image, content trust, and vulnerabilities from the register. You can choose to block or allow the deployment of an image that are stored in other registries. So these are the typical things that you can integrate with your toolchain to make it more secure. Apart from the usual build, you may want to add unit tests and ensure the Docker image signing is there. Check for vulnerabilities, and before deployment, you have to ensure that you have to do a pre-check on the signatures and then deploy the image to ensure security. And the next part is vulnerability scanning. We face attack vectors like OS vulnerabilities, for example, unpatched libraries or vulnerable kernel versions, or be it application weaknesses like SQL injection, buffer overloading, or cross-site scripting. With containerization, every layer in the container is just a link in the chain. The containers that you produce can be used as the base for another container, and so on, with every link in the chain that is susceptible to attack vectors and threats. So that's when vulnerability scanning comes into the picture. We scan the container images before deploying. We use open source tools like OpenScape, or when we are going with a cloud provider, if you're running a managed service on some cloud, we use the inbuilt security scanning that they provide. This is one feature on IBM Cloud called Vulnerability Advisor which performs a typical scan on our container images and gives us back a status. So right now, this is a demo application where it's saying do not deploy, and it has 173 vulnerabilities and so configuration issues. So this vulnerability scanning provides us with a typical assessment that gives us a list of CVEs and configuration issues. So CVEs, common vulnerability and exposures, it's a list of publicly disclosed environment, uh, publicly disclosed list that actually describes us what are the information security vulnerabilities that are available. And every time we are presented with a new threat, this list is automatic. This list is being updated and maintained. So vulnerability advisor is something that scans our container images and comes back to us with CVEs. If you see, each CVE comes with a unique ID. So it is giving us that so and so container environment has this CVE vulnerability. There is no policy that has been applied, and it is also helping us with a quick fix. It's asking us to update a unpatched library. And similarly, most often we forget to keep in mind the configuration issues with so and so container image. Vulnerability advisor is something that also looks into the configuration issues that are present in an environment and comes back with how to resolve that, how to address that configuration issues. So in a typical DevOps pipeline, we'll have to make sure that the containers are, the best practices around security are involved in the pipeline before actually deploying it. This is the security concepts around the topic. And finally, we would want to close the session by introducing to something called IBM Developer Advocacy. Saurav here and myself, we are developer advocates. There are multiple ways of engagements that we do with developers: meetups, workshops, office hours, hackathons, webinars, proof of concepts. These are some of the engagements that we do where we customize some of the hands-on on emerging technology like data and AI, cloud native, DevOps, integration, etc. And enable your developers on various technologies. If you are interested, please reach out to us. And until then, thank you. And I'm hoping that you stay safe.